After completing this lecture, the student should be able to do the following. List the various components of power converter system with block diagram. List the ideal characteristics of power switching devices. List the characteristics of practical switching devices. The operations of the power converters are based mainly on the switching of power semiconductor devices, and as a result, the converters introduce current and voltage harmonics into the supply system and on the output of the converters. These can cause problems of distortion of the output voltage, harmonic generation into the supply system, and interference with the communication and signaling circuits. It is normally necessary to introduce filters on the input and output of a converter system to reduce the harmonic level to an acceptable magnitude. The application of power electronics to supply the sensitive electronic loads poses a challenge on the power quality issues and raises problems and concerns. The input and output quantities of the converters could be either AC or DC. Factors such as total harmonic distortion, that is THD, displacement factor, that is DF, and input power factor, that is IPF, are measures of the quantity of a waveform. To determine these factors, finding the harmonic content of the waveforms is required. To evaluate the performance of a converter, the input and output voltage and current of a converter are expressed in Fourier series. The quality of a power converter is judged by the quality of its voltage and current waveform. The control strategy of the power converters play an important role in the harmonic generation and the power quality mitigation and can be aimed to minimize or reduce these problems. So power flows from the control side to the output side. The waveforms at different terminal points would be different as they go through processing at each stage. It should be noted that there are two types of waveforms, one at the power level and another from the low level signal from the switching or gate control generator. These two voltage levels must be isolated from each other so that they do not interfere with each other. So from the figure, we can see a generalized power converter system in which the power converter is at the center. The input is provided by the power source. In between, you can see an input filter circuit connected there. Further, the output of the power converter is given to the output filter, and the switching and the control signal generator provide the gating switches to the converter switches. Power electronics is an interdisciplinary subject, and the design of power converters need to address the following. Power semiconductor devices, including their physics, characteristics, and drive requirements, their protection for optimum utilization of their capacities. Power converter topologies to obtain the desired output. Control strategies of the converters to obtain the desired output. Digital, analog, and microelectronics for the implementation of the control strategies. Capacitive and magnetic energy storage elements for energy storage and filtering. Modeling of rotating and static electrical loading devices. Ensuring the quality of waveforms generated and a high power factor. Minimizing the electromagnetic and radio frequency interference. Last, optimizing cost, weight, and energy efficiency. So here we can see the block diagram of a typical power converter, including the isolation, the feedback, and the reference signal. Coming to the ideal switch, the characteristics of an ideal switch are as follows. In the on state, when the switch is on, it must have the ability to carry a high forward current IF tending to infinity, a low on state forward voltage drop V on tending to 0, and a low on state resistance R on tending to 0. Low R on causes low on state power losses P on. In the off state, when the switch is off, it must have the ability to withstand a high forward or reverse voltage VBR tending to infinity, a low off-state leakage current I off tending to zero, and a high off-state resistance R off tending to infinity. High R off causes low off-state power losses P off. During the turn on and turn off process, it must be completely turned on and off instantaneously so that the device can be operated at high frequencies. Thus, it must have a low delay time Td tending to 0, a low rise time Tr tending to 0, a low storage time Ts tending to 0, and a low fall time Tf tending to 0. For turn on and turn off, it must require a low gate drive power Pg tending to 0, a low gate drive voltage Vg tending to 0, and a low gate drive current Ig tending to 0. Both turn on and turn off must be controllable. Thus, it must turn on with a positive gate signal and should turn off with a negative gate signal or with a zero gate signal. For turning on and off, it should require a pulse signal only, that is, a small pulse width with a very small width Tw tending to 0. It must have a high dV by dt tending to infinity, that is, the switch must be capable of handling rapid changes of the voltage across it. It must have a high di by dt tending to infinity, that is, the switch must be capable of handling a rapid rise of the current through it. It requires a very low thermal impedance from the internal junction to the ambient, that is RIA, tending to 0 so that it can transmit heat to the ambient easily. The ability to sustain any fault current for a long time is needed, that is, it must have a high value of I squared T tending to infinity. Negative temperature coefficient on the conducted current is required to result in an equal current sharing when the devices are operated in parallel. Low price is a very important consideration for reduced cost of the power electronics equipment. Coming to the characteristics of a practical device, we can see in the figure it's a controlled switch. The graph shows the waveform for the voltage across the switch, the current across the switch, the gating current, the gating voltage, and the power switch across the switch. During the turn on and turn off process, a practical switching device requires a finite delay time Td, rise time Tr, storage time Ts, and fall time Tf. As the device current ISW rises during turn on, the voltage across the device, that is VSW, falls. As the device current falls during turn off, the voltage across the device rises. The turn on T-on of a device is the sum of the delay time and the rise time, whereas the turn off time of a device is the sum of the storage time and the fall time. In contrast to an ideal lossless switch, a practical switching device dissipates some energy when conducting and switching. Voltage drop across a conducting power device is at least on the order of 1 volt, but can often be higher up to several volts. The goal of any new device is to improve the limitations imposed by the switching parameters. Power losses increase during turn on and turn off of the switch because during the transition from one conduction state to another state, both the voltage and current have significant values. The resultant switching power loss PSW during turn on and turn off periods is given as in this particular equation, where Fs, that is equal to 1 upon Ts, is the switching frequency. Td, Tr, Ts, and Tf are the delay time, the rise time, the storage time, and fall time, respectively. Therefore, the power dissipation of a switching device is given by Pd is equal to P on plus PSW plus Pg, where Pg is the gate drive power. The on-state power P on and the gate power PG losses are generally low as compared to the switching loss PSW during the transition time, when a switch is in the process of turning on or off. The gate power loss Pg can be neglected for all practical purposes while calculating the total power losses Pd. The total amount of energy loss, which is the product of Pd and switching frequency Fs, could be a significant amount if the switch is operated at the high frequency of kilohertz range. So, from this particular lecture, we discussed the block diagram of the power converter system, the components of a power converter system, the characteristics of an ideal switch, and the practical characteristics of a power switching devices. Thank you.